we looked at, well, why you would actually care about, inference on the internet. We discussed a little bit various communication paradigms. So I'll start this off with an application. And this application serves two purposes. First of all, many of you might have read at some point about a Bayesian spam filter. And the Bayesian spam filter is actually not very Bayesian at all. It's just NaiveBayes, which a lot of journalists mistake for being Bayesian. And so they misquote it, and then they say, this is running a Bayesian spam filter. NaiveBayes is actually extremely naive, and it's really simple to implement, which also means it's a pretty good reason to compare against, at least if you want to see how well your algorithm is doing relative to a simple baseline. Can be nicely parallelized and so on. So it has a lot of nice properties. On top of that, it'll serve a little bit as a motivation for then some density estimation techniques that we'll be discussing in a moment. Okay, so let's do a bit of spam filtering. So let's look at the NaiveBayes spam filter. So the key assumption in NaiveBayes is that all the words, the occurrence of the words, conditioned on whether an email is spam or not, are independent of each other. So last week, we discussed an AIDS test, right? And we have basically two, quote, words, namely the outcome of test 1 and the outcome of test 2. And we assumed that conditioned on the health status of the patient, these outcomes would be independent. What we're doing here is we're treating the absence or presence of every single word in the dictionary as a test. And so if a word is present or if it's absent, it tells us something about whether this is more likely to be spam or not. So for instance, all of us probably know that if the word Nigeria or Viagra occur, it's a pretty high chance that this email is maybe about spam, right? And if we make this assumption, it's obviously clearly horribly wrong, then we can just apply Bayes' rule. Instead, what we can do is we can compute P of spam, given all the words, is then proportional to P of spam times the product of P of wi given spam. So we basically check how well our hypothesis of spam or ham fits all the words that we see, times the prior probability of actually seeing spam, and that's proportional to P of spam given the email. So the approximation is here. The step from here to there is exact. And so then all we have to do is we just have to compute those probabilities, right? And we need to get P of spam, and we're done. Just to give you some idea of, what that might mean is, you could have your standard spam phrases like, right? So, but this one is also equally likely, which is essentially a combination of the top three. So let's just rewrite that as a graphical model before we go into the algorithm details. So here's what we did. I said, well, P of spam, conditioned on spam, I emit the words possibly W1, W2, up to WN. And so this is a graphical model, a directed one. Basically, this depends on that. And since it's kind of awkward to always, repeat all those nodes and put the dots in between, statisticians have invented the for loop. It's this thing here. It's called a plate. So basically, whenever you see a plate, I mean this. Repeat. So it's exactly the same thing as a for loop in computer science. The only cool thing that you can get away with as a statistician that would be sort of a no-no in CS, in programming, is if you have intersecting for loops. If you have two for loops which share some of the variables but not all of them, programming that is usually not quite that much fun. The corollary of that being, if you have an intersecting for loop in your statistical model, once you implement it, you actually need to deal with that. But usually, these things will map directly into a for loop somewhere in your code when you implement an inference procedure. Okay, so this thing here, and I would have to actually write times p of spam, maps into this. Sometimes I drop that index variable if it's clear what is to be repeated. Okay, so now, how do we get p of w given spam? Let's have a look at a very simple algorithm. So the simple algorithm goes as follows. For each document, so x and y pair, so x is a vector and y is just an attribute, you just aggregate these label counts given y. Right. For each feature xi in x, aggregate the statistic for xi and y for each y. So we count how many spams, how many hams we receive. For each word, we count how many times it occurs for spam, how many times it occurs for ham, for instance. And so then, once we've done that aggregation over our entire data set, so this is very easy, we come up with a model of x given y. And what we do is we, for instance, use Parson windows or the exponential family. And then afterwards, we can do this. So it's really simple. And if it's just a matter of traversing somebody's mailbox, you can easily do that on a laptop. Now imagine I had a really large amount of data. Then how would you go and parallelize it? Does anybody have a suggestion? Which part can be parallelized? So the counting part can be parallelized. Can I parallelize that too? Yes, because for each word, I can build my model separately. Because once I've done all the counting, I know how many times that word occurs when there's spam or ham. And since I made the assumption that the outcomes are independent of everything else, well, I can parallelize. So here's a simple MapReduce program which will do the trick. So the mapper basically goes through all the documents, so it breaks them up into chunks, and it passes through all the data. And then we reduce. So map, aggregate the statistic for each document, and send the aggregate to the reducer. The reducer combines all the subcounts for a word from all the mappers. So each reducer now only works on a subset of the words. The mapper worked on a subset of the documents. That's the key trick. And once I have that, well, I just come up with my density estimates, and then we aggregate the global model, and it's ready for consumption. That's MapReduce NaiveBayes. Does anybody have a question about that at the moment? Okay. Now, let's just look at what happens in practice. So let's take the very naive version of a NaiveBayes. We only take two classes, spam and ham, and we only check whether certain features are present or absent. So this is even dumber than what I mentioned before. And so now the algorithm is really just counting. So the probability of, let's say, xi, whether the particular attribute is present or not, being true, given y, is just the number of times this particular attribute occurs for y divided by the overall number of times y occurs. And p of y is just number of times I see, for instance, spam divided by the total number of emails. So then, well, what I get is I get p of y given x is proportional to that ratio times the product of these ratios. Right? These are very simple numbers. Can anybody see a problem here? What could possibly go wrong if we did this? Perfect. So the thing that could go wrong is, for instance, we see a word that never occurred before. In this case, well, this number is going to be 0. Okay, well, fine, maybe for the ham it's not going to be 0. If the word actually never occurred, it's going to be 0 in both cases. And we have a real problem. I can make it worse is if I have a word that never occurred and one that always occurs. In both terms we'll get 0, right? So what happened? What happened is that basically we used the empirical frequency estimates and treat them as the truth. And something's clearly wrong here because we are basically overconfident in these 0 probability events. One way of dealing with that is by what's called Laplace smoothing. So this is exactly what I discussed before. What if these things are 0 or they're in? And what I can do is I can just add a small constant to all those counts. And then, they don't work out to be 0 anymore. Sounds like a, a really crude hack. Turns out that this is not such a terribly crude hack, but it's actually a pretty well reasonable model for estimating probabilities. It goes back to Monsieur Laplace, and that's why it's called Laplace smoothing. Now I'll show you now what the theory behind it is. The theory behind it is actually very simple. It's basically conjugate priors. Okay. Now let's go and look at estimating probabilities. Does anybody have a question so far? Today the room is very quiet. Yes?
Does the theory of conjugate priors also extend to more complicated smoothing?
Absolutely. So the notion of conjugate priors is basically that, okay, without giving too much away already, the idea is that your posterior should look like your prior. That's the general idea of conjugate priors. So what that means is that your prior effectively should look like some actual data that you observed, or in other words, fantasy data. What this also means is that you can easily cook yourself a conjugate prior by just taking a maximum likelihood method. And so you just do your standard empirical maximum likelihood approach. But what you do is you add fantasy observations to it that you believe ought to be true. Now, in most cases, this is not going to be computationally very nice. And in some cases, depending on how you do this, you might not get a terribly well-behaved prior out of this if you just generate fantasy data in an unsophisticated manner. But there are some ways how you do this. And a certain class of models, namely exponential families, this actually integrates out very nicely, and you can build very beautiful yet complex systems with it. And we'll be making a lot of use of that in the following. It's a very good question. Thanks. Okay, so let's estimate probabilities. Start with something very simple. So let's say we have two outcomes, heads and tails. So then I can just model the data likelihood by P of x, parameterized by pi to the n1 times 1 minus pi to the n naught. N1 is the number of times I see a 1, n naught is the number of times I see a 0. And then I can do maximum likelihood estimation, right? It's a constraint optimization problem. Maximize this expression here, subject to the constraint that pi be contained in the interval between 0 and 1. Now, and so how can we deal with that constraint? Well, one way is we reparameterize pi. We just say, well, P of x parameterized by theta is e to the theta x divided by 1 plus e to the theta. This looks like an extremely non-obvious way of reparameterizing a simple variable that's to be constrained between 0 and 1. First off, you can check that it actually does the trick. So if I send theta to infinity, this all goes to 1. If I send theta to minus infinity, it all goes to 0. Okay, so we are fine here. The way how, in a moment, I'll show you how you can derive this is by basically saying, well, P of x parameterized by theta being proportional to e to the x times theta. And then the denominator is just there to make sure that probabilities always sum up to 1. But okay, be it as it may, if this is our parameterization for the likelihood, if I take derivatives, that's what I get. Namely, theta is the log of n1 over n0 plus n1. In other words, p of x given equals 1 is given by the ratio between the number of times a 1 occurs divided by the number of times a 0 or a 1 occur. Now, this is something that probably, an elementary school kid would come up with as a probability estimate. Let's say you toss the coin 10 times, 5 times it comes up heads, 5 times it comes up tails. So then the kid might say, okay, yeah, the probability of heads is 1/2. Right? You would do that. That's the algebraic version of it. Now let's just look at the derivation a little bit more in detail because it actually tells us something.
Question?
Yep.
Do you allow a coin to come up a third head and 2/3 tail?
In the conjugate prior, I do that. But for the model here, I don't, because I assume that these are discrete events. And no, I'm not assuming that the coin can end up on its edge either. But that would be a nice assignment for you to come up with a model that incorporates all three. And based on the slides that you're going to see afterwards, this should be trivial for you to do. Okay, so let's just have a look at the algebra here. So p of x parameterized by theta is just the product of I going from 1 to n, p of xi given theta, right? Now, I can write it as such, right? And if I want to maximize this, quite often it's a good idea to take a log and then maximize it. Now, taking logs makes these pesky exponentials go away, right? And just get theta times sum over xi minus n times log of 1 plus e to the theta. So actually, if you look at this function here, you'll see it's a convex function. And that's not a coincidence either. We'll see that all those functions that look maybe a little bit messy and that occur in an exponential family will be convex. And we'll prove that in a moment. Now, if I take derivatives, well, d theta, it's just sum over xi minus n times e to the theta divided by 1 plus e to the theta, right? And now dividing by n gives me exactly the condition that I talked about before. This must be probably the most complicated derivation you've ever seen to estimate a binomial probability, right? I did that for a reason, because afterwards these will be sufficient statistics in general, and you should check at home that the same algebra that I showed you here for the simple case will go through in general. Okay. And this is the neat thing. This is really our empirical average. And what we will show is that basically what this model does is it requires that the empirical average matches the expectation. And there's a much more complicated derivation yet, which then shows that it's a maximum entropy distribution under these conditions. Okay. Now, discrete distribution. So let's say n outcomes, like from which country a user is from. So I want to get the data likelihood, so I get p of x parameterized by pi. It's pi to the ni. Now, I could equally well rewrite it as a constraint optimization problem, or I incorporate the constraint directly in the probability. And this is like the standard softmax function, right? Basically, if I took the log of that, I would get the softmax out of it. So it's e to the theta x divided by the sum over e to the theta x prime. And that, again, just ensures that things are properly normalized. Now, taking derivatives yields that theta I is the log of ni over sum over nj. In other words, again, it's the number of times I see a particular event divided by the total number of event counts. Okay. Same derivation as before, just, okay, rather than 2, we now have k outcomes. Yep?
So
Okay, so the question is, would it be more difficult to solve the optimization problem without that constraint? You would probably not have a convex problem anymore. You would need to argue that the solution is actually unique and well-behaved. Let me put it this way. I'm not saying that you can't do it, but you're probably going to have a bit more fun trying to get the answer. So at least you'll need to introduce a Lagrange multiplier and so on. So effectively, you will introduce the constraints anyway. So it's going to be a little bit messy. But yes, you could do it. The more interesting thing is once we go from just discrete events over k outcomes to general marginal polytopes in a graphical model, one of the approaches becomes an utter nightmare, and the other one is a bit less of a nightmare. So it's, in general, more effective if you deal with it in this way. So for instance, if you have a normal distribution, your constraint will be that the eigenvalues of the matrix must never be negative, right? And that already gets even more fun. Okay, so let's just see how well it works, just to get a bit of an idea. So let's just toss the dice. And I tossed it 12, 24, 60, and 120 times. The red line, shows me where. Okay, so here it should be a 2, there it should be a 10, where the uniform distribution should be. And I can assure you this is a perfect dice. Python at least claimed it was one. And no, I didn't toss it myself. I've gotten this question before. You write a for loop that goes up to 120. No, it's based on the real questions I got asked. So, and what you can see is that, actually with 24 cases, well, it's not terribly good yet. Even with 60, like if you look at the 6 at the 3 here, it's actually way more frequent than it should be. So what this tells you is that even with a perfect dice, you can get fairly strong deviations. And probably if you were playing a game and the 3 came up that many times, you would probably start getting a bit suspicious of what's going on. And actually, this is perfectly reasonable. It's just, what happens if you roll a dice? Yeah, these are the big worries, right? You roll a dice 12 times and you don't see a single 2. Okay. Why am I showing this? Quite often in machine learning, we might have a number of parameters that's equal or larger than the number of instances that we see, right? Here we have a number of samples which is already twice as large as the number of parameters, right? Here we have something that's 10 times as large as the number of parameters, actually a little bit larger because we have the summation constraint. Yet still here we are off by a factor of 2, right? So beware. Things converge more slowly than you would hope for. So, how do we fix it? Well, for that, we'll need a little bit more theory. And that'll get us exactly to conjugate priors and penalized likelihoods and so on. So for that, we need exponential families. Now here comes the algebra. We take a density function, like p of x parameterized by theta, is given by e to the phi of x dot theta minus g of theta. And this g of theta is this log expression, and that's the case because I want to make sure that things are properly normalized. Let me just set to screen. Let me quickly derive this. So suppose I want to have, okay, it works out. I want to have p of x is proportional to e to the phi of x dot theta. Now I need to ensure that the sum over x of p of x equals 1. Right? So I can do this by saying that, well, this needs to divide by some z. And so I get that sum over x e to the phi of x dot theta divided by z equals 1, which I can solve to say z is this. And now I define g of theta. I just define it as, well, the log of z. Okay. Now once I have this and plug it in up here, I get exactly my exponential families expression. Right? And the nice thing is, this works for any phi of x. And the key question is whether I can solve this integral here, the sum. If I can compute the sum here, everything's fine. In many cases, this will be a key problem of inference. Now, this log partition function has a couple of very nice properties. One of them being that it generates the expectation, and the second one that it actually generates the cumulative, the variance. Okay, so can somebody tell me why this implies that G is convex? Yes? Perfect. Exactly. Because the variance of a random variable has no negative eigenvalues, so therefore it means that the second derivative of this function g has no negative eigenvalues, hence it's convex. Okay. Now, I will actually quickly show how to derive this, because it's kind of a fun derivation. Okay. So recall, we have g of theta being the log of sum over x e to the phi of x with theta. From that it follows that d theta of g of theta is, well, the log means we get this in the denominator. So we get the sum over x e to the phi of x with theta. And here we just need to apply the chain rule. So sum over x, phi of x times e to the phi of x with theta. Let's just sum over x primes here. We'll need that in a moment. Okay. Now, let's look at this term here. This equals p of x parameterized by theta, right? So I get sum over x, phi of x, times p of x parameterized by theta, which is nothing else but the expectation of x drawn from p of x parameterized by theta of phi of x. Okay. Now for the variance, we get a similar property. Basically, you take another derivative of this expression here, and then you need to actually plug this back in again, and it's a little bit more algebra, so it'll be a few more lines. If you've never done this before, you should do it once in your life, and there's no need to do it more than once, but it's a good idea to do it once. It'll also give you a bit more confidence in dealing with exponential families. Okay. Any questions about the derivation so far? Okay, good. Okay, so let's look at a few examples. So the simplest one we already saw before, the binomial distribution, right? Phi of x is x, and x is drawn from the set of 0 and 1. A discrete distribution would be if we just have phi of x is ex. That basically means we have the unit vector x. And a more interesting one is where we have a Gaussian. Actually, let me quickly show you why we get the Gaussian. That might be kind of instructive. So everybody knows what a Gaussian looks like, right? So we have p of x is given by 1 over 2 pi. Oh, thanks. 1 over 2 pi to the d over 2 determinant of the covariance matrix to the 1/2. So, okay, I might just keep it there. What would prefer to see two screens of the same content most of the time versus who? Okay, good to know. I think I'll just leave that there for the moment. So we have this mess here, which just makes sure that things are properly normalized, times e to the minus 1/2 x minus mu transposed sigma inverse x minus mu. Now what we can do is we can expand this. This is a second order function in x, right? So this is nothing else but, okay, x transposed, the trace of this, times sigma inverse mu. It's probably the most complicated way how you've ever seen. Sorry, no, there's no mu in it. Then we have plus, well, x transposed, and here we have sigma inverse mu. And then we have some other terms, basically that only depend on mu and sigma. So what you can see now is we have basically a term which is linear in x transposed and one that's linear in x. So if I have an exponential function which uses x transposed and x, and I pick the right parameters, then I'm going to get exactly a Gaussian. If I pick the wrong parameters, my integral diverges. And it turns out that the right parameters form a nice convex set. Okay, that's the Gaussian. More
two sets of parameters, the x transpose as well as the x.
So why do I need two sets of parameters? Because I have a linear and quadratic term in x. The quadratic term ensures, deals with the covariance. The linear term deals with just the mean offset, shifted accordingly. Funnily enough, this year at ICML, there's another paper about heteroscedastic Gaussian process regression. And it completely ignores the fact that you can actually do it efficiently through the exponential family. Yeah. We had that 5 years before them in the same conference. They're not even aware of it. Okay. There's a few more, Dirichlet, Beta, Gamma, Wishart. They all belong to the exponential family. A good place to look them all up is if you go to Wikipedia. So now, there are more than that, but basically anything for which you can solve an integral, you're in good shape. So normal distributions. Well, everybody's seen a Gaussian before, I hope. The a Poisson distribution you may or may not have seen before. It's a distribution of discrete events, and it's kind of special in the sense that it has this strange x factorial normalization term in here, right? So this is something that I completely swept under the carpet before, that you actually have a measure that's associated with the domain of the random variables that you observe. In this case, the measure is just 1 over x factorial. And then the remainder now is something that is, linear in, well, x, right? So you have basically e to the x times log lambda minus and then some normalization, and that ensures that you are again in the exponential family. Let me quickly rederive that. So here we have p of x parameterized by lambda is just lambda to the x e to the minus lambda divided by x factorial. Now I can go and just write this as 1 over x factorial, so that just remains unchanged, e to the, well, now what do we get? X times log lambda minus lambda. Now I'm going to reparameterize this as theta, and this then becomes e to the theta. So I get 1 over x factorial e to the x times theta minus e to the theta. Okay, and this is my log partition function. Okay. Yeah, the computers don't like it. Yeah. So in that case, now it becomes really easy if I want to compute the expectation with respect to x, right? So if I want to get e of x parameterized by theta, I know that this is just d theta of g of theta, which is just, well, d theta of e to the theta is just e to the theta, right? So now I've computed the expected value for a Poisson distribution without ever really touching the Poisson distribution besides worrying about the normalization. So I can now compute, for instance, second order moments, and it turns out even higher order moments in just the same way by just taking derivatives. This is really handy. So I've gotten completely over the issue of, computing any expectations. I just need to take derivatives, and that's just so much easier. I can just throw that into Maple or Mathematica or whatever, and problem solved. So once you solve the one hard thing, which is computing the log partition function, you're home. Except that in some cases, that's actually NP hard. OK, good. Moving on to the beta distribution. That one's kind of handy, right? So if you have a distribution on a unit interval, you want to have something that's peaked somewhere in between or, biased to either end. Well, that one does it for you. It actually also is the conjugate to the binomial, and we might make use of that for later on. And here's a really nice one, the Dirichlet distribution, which is the generalization of the beta, as it turns out. And that one is actually, if you think about it, a distribution over distributions. So if you look at the domain on which it's defined, this is a simplex. It's actually a probability simplex. In other words, the sum over the points of the coordinates of these points here on this simplex sums up to 1. So what I now get is a distribution over distributions. It's a subtle point. It's not a distribution over parameters anymore. It's a distribution over distributions. So for instance, I might have a distribution which, assigns most of the mass here to the first event, and I might be very uncertain about the distribution itself. Or I might be very certain about the distribution, but very uncertain about its outcomes. So, important distinction. You may have a lot of uncertainty about various outcomes, but be fairly confident about the distribution that generates it. A lot of people mix that up. Let's just do maximum likelihood. Let's just write the negative log likelihood for a moment. Okay, so this is just, sum over I going from 1 to ng of theta minus phi of xi parameterized by theta, which I can then take derivatives of, right? Okay, that actually should be an n here, right? Sorry. It's just, n times e to the e of phi of x. That's just our derivative, that's what we had before. Minus 1 over m sum over I going from 1 to n phi to the xi. And what it really means is that, well, we go and pick the parameters in such a way that the empirical average matches the expectation. Is this a good idea? Well, in general, maybe not quite such a bright idea because our empirical averages might not be perfectly accurate. As an aside, this solution is also what you get if you ask for the maximum entropy distribution that matches the empirical average. So the exponential family can be derived from the condition of having a maximum entropy distribution that matches certain statistics. That's why you get exactly those exp expressions. If you then say, well, I want to satisfy that only approximately, I get a penalized maximum entropy where the penalization goes with some Banach space norm. Let's just look at conjugate priors. The trouble is, unless we have a lot of data, the estimates are really weak, and we saw that before with the dice. And the other good thing, however, is that usually we actually have a pretty good idea where to search, right? We might have actually seen such data before. And one way of dealing with it is we just add fake observations. So for instance, if I play dice with Manfred, I know Manfred is really trustworthy, and so I give him the benefit of doubt of essentially having played maybe 100 fictitious games with Manfred before. Now, if it turns out that actually he is quite devious and has tainted the dice, eventually I'm going to wisen up to that fact, but it'll take me a lot longer. But it'll also take a much longer before I start assuming that Manfred is actually a devious person rather than the honest person he actually is. So what we do is we add fake observations, and here's something really beautiful that happens. A conjugate prior says that, P of theta, so my prior, should look exactly like P of fake data given theta. So it should just look like a posterior. It should just look like a likelihood, sorry, not a posterior. So if we have this, then P of theta given x, I can just expand it, this Bayes rule. It's just my likelihood times the prior. Now, however, since I'm assuming that they're all IID drawn, I can just take the union of those two sets. So what it means is that now my posterior looks like a likelihood term where I've thrown in fake data in addition to real data. So I hope that solves your question from before a little bit about conjugates. So I can really invent data, invent instances, throw them in, and that gives me a conjugate. And what it means here is that inference, and you can derive that without ever looking into the algebra once you know this, is that before that we had those averages 1 over n sum over phi of xi, and they now become 1 over n plus m. M is the number of fake instances. And I downweight the actual observations and add the fake counts and the fake mean to it. These can now be fractional. There's no reason why, my conjugate needs to be, proper integer. So for instance, if I were to suspect Vichy to be cheating a lot at playing a dice, I might only give him the benefit of doubt of having played maybe 0.1 game with him before. Right? that's something that you can then adjust with your prior fairly efficiently. So there's a fake mean, fake count. That's how you can turn everything into a conjugate very, very easily. So let's look at Gaussians, because there it's a little bit less trivial, right? So just recall that the mean and the variance are given by, the expectation of x and the expectation of x squared minus the expectation of x squared. Right? Now, in that case, the maximum likelihood estimate is just, 1 over n sum over xi, and sigma squared is just 1 over n sum over xi squared minus mu hat squared. Okay. Now, if I were to do a map estimate, things get a little bit more interesting. I now end up smoothing, so that's just like our Laplace smooth mean that I would have before. So in that case, my conjugate was that I have a normal distribution with 0 mean and unit variance. So that's why I don't get anything else but just the empirical average. So this is just a standard shrinkage estimator, but it gets shrunk less the more data I actually observe. And here, for the variance, what I do is I go and take my empirical second order moment. My smoother to that is I just add, some amount of ones to it, and I subtract, mu hat squared, which is now this new quantity here. So this, for instance, allows me, even if I have very high dimensional data, to make sure that my eigenvalues are never 0. So even if I have like 1,000 dimensional data and only 100 instances, in which case this clearly would have, would be rank deficient. It would have at most rank 100. After this conjugate smoothing it, I'm guaranteed to have full rank. This is a simple way of smoothing Gaussians. Okay. Does anybody have questions about this? Because it's a rather subtle point. Okay. Now here comes the really fun part, collapsing. So if you think about it, well, we required that P of theta is proportional to P of fake data parameterized by theta. However, this means that at some point I will have to have been able to actually compute the integral of this expression d theta, right? After all, if I have a conjugate prior, I would like it to be normalized, right? So at some point somebody must have computed this integral. Now, if I want to do a prediction, namely P of a new little x, given all the previous data that we've seen, I can now expand it, right? It's P of x given theta times P of theta given all the previous data d theta, right? So far it's okay. Now I can expand it further. It's proportional to P of x given theta times P of da 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 da, right? Which is now equal to P of x union the actual data that I observed, union the fake data given theta d theta. Okay. Now why is this nice? Because this integral I know how to solve. At least somebody else will have done that before. Now if you had used that insight 5 years ago, you would have been able to write a paper on Bayesian sets. So that's a paper by Heller and Garamani, which uses exactly this idea to say, well, look, if I have this, then I can check how reasonable some observation little x expands another set of observations. It's very trivial to do. All I do is I just ask, how well does it fit into that set? And if I have several sets, I can check for each of those sets how well does it fit in. And this gives me clustering, right? And then I just add the points as I go along. That's essentially a clustering algorithm. We will need that type of reasoning over and over for the rest of this lecture. So if you have questions about it, now's a good time to ask and to wake up. Any questions? Yeah? Pardon?
Why is it called collapsing?
It's called collapsing because I'm integrating out the unobserved parameter. So you basically remove one parameter from your joint distribution. The price that you pay for that is that now the distribution in all the random variables is not conditionally independent anymore. So now it's not conditionally independent on my latent parameter, and I have all the xi's and the fake instances and all that conditionally IID, but they're now just exchangeable. That actually connects to something fairly interesting called De Finetti's theorem, which says if I have an exchangeable set of random variables, then there must exist such an expansion. I'm not going to go into that in detail this time, but this is one of the arguments that people quite often use for reasoning why they are Bayesian. You had a question before.
So this is basically the posterior predictive distribution, right?
Correct.
And I've seen this used quite a lot in social sciences for model checking.
Yeah.
How were you trying to say that it can be used in higher dimensions? And I guess it's about model checking as well in some way.
Okay, so actually this is good news that social scientists use that for model checking. I wasn't actually sure how much model checking was being done in social sciences. So if I have higher dimensions, then in many cases that integral here may not be easily solvable anymore. And when that happens, then, well, I can replace this integral in some cases by maybe Gibbs sampling or some other Monte Carlo procedure in order to come up with an approximate version of that integral. And that's where a lot of the interesting inference in graphical models, for instance, comes into play. In some cases, these expressions here may actually be non-parametric. So P of x given theta may actually parameterize a very general family of distributions. And there are function classes which give you necessary and sufficient conditions for being universal approximators. So Peter Orbans last year, or possibly 2 years ago at NIPS, had a nice paper on non-parametric exponential families, which discusses the theoretical aspects of that in a fair amount of detail from the measure theoretic aspect. So if you love measure theory, you'll enjoy the paper. The converse, unfortunately, is also true.
What is the reference, please?
Peter Orbans, and look for NIPS, possibly. So, and he has a long tech report on that. So just look for that paper. Okay. Any other? Yes.
In practice, normally the data is not available. So, which methods that you can use to estimate or approximate the probability of checking the
Okay. Okay. So you're absolutely right. In general, this is not available as data. So if I can integrate it out, I'm in good shape. And this happens exactly when my distribution is nice and simple. I can perform sampling where I draw from theta, right? I draw from P of theta given x. Then that gives me, an approximate solution to the integral. I might actually do something outrageously horrible and just say, well, let me compute the mode of P of theta given x and treat that as my correct parameter and then plug it in here. This is what's called the maxima posteriori estimation. And even though it sounds absolutely outrageously horrible, it still works quite well. Basically, most of Gaussian process classification algorithms use exactly that. You can view a lot of SVM-style estimates as doing that very thing. So even though it's really horrible, it still works well. You might have more general sampling procedures. You might have a variational approach. I'll be discussing some of these methods in the following when we look at inference in intractable graphical models. But thanks. It's a very good question. Any other questions? I think it's probably actually a good time to conclude with just 2-3 slides about how conjugate priors behave, and then we'll have a brief break. So conjugate priors, here's what we get. And can somebody spot the bug? Or maybe it has been fixed by now. I think it's been fixed. Okay, so what we have here is we have some counts, some outcomes. for 1 to 6. And here are the maximum likelihood estimates for the probabilities. And there are the maximum posteriori estimates. And what I did is I showed you the map estimates if I assume that I've only played 6 games with that person before, and here it would be 100 games. So I trust this person a lot less than that one. And what you can see is that in the map estimate, everything gets pretty much smooth to the uniform distribution. If I have a map estimate with only 6 instances, then it's a lot less so, and the maximum likelihood estimate is really rough. By the way, if somebody could get me some batteries after the break, that would be terrific. So a good rule of thumb is you need at least about 10 data points per parameter. Then your estimates are not going to be too horrible. Here's an example, an honest dice and map. So you can see MLE is actually quite horrible. Map is pretty good. And this, of course, is the warning. If I have a tainted dice, then the maximum likelihood estimate is going to pick up on it very, very early, whereas map needs a lot of data. And here's an alternative. So rather than saying, well, I have a conjugate prior, I could just require that my natural parameters be small or sparse or in some other way well behaved. In other words, P of theta is maybe proportional to e to the minus lambda norm of theta. Or this can actually be a gauge function, or here just L2. And then the posterior looks exactly like what we had before, but we had to have this normalization here. And then I get a convex optimization problem. And a lot of Gaussian process classifiers or conditional random fields use this parameterization rather than the conjugates. This is sometimes easier to deal with because it's very easy to just say, well, hey, my parameters better be small and everything be close to uniform distribution. And you could also have something sparse. You could have an entropic penalty, and then you would get a multiplicative update algorithm. And that would make Manfred much happier, I think. So that's actually the end of this unit. So I hope I showed you a little bit of basic statistical tools, how to estimate probabilities, and showed you the exponential families. So what we're going to do next is you're going to learn about the connection between the chicken and the egg. Who came first? So we have a 5 minutes break now. Oh, we have lunch break. Oh, even better. Still only 5 minutes, of course.